everyone. Can you hear me all right? Yay. Who said that? Who's talking? Welcome to Griffith Observatory and to All Space Considered. How many of you have been to All Space Considered before? Okay, welcome back. And how many of you have never been to All Space Considered? Okay, that's kind of crazy. And of those of you who have never been here before, how many of you came because a friend said, come with me, I got to show you this thing? And how many came because you saw it on a website, any website? Yay, website. And how many of you came because you saw on a line, this is David's favorite, you saw a line, you got in and, hey, something's going on there, I'm just going to get in this line.
Nobody tonight.
And we always love to ask anybody, see it in a newspaper, a piece of paper with print on it. Once again, the number is 0. Okay,
Black and white and red nowhere.
Yeah. Oh, ooh. So with that, I'm a little embarrassed to say my name. No, I'm Dr. Laura Danley. I'm the curator of Griffith Observatory and your host for this evening. And with me, as always, is Dr. David Reitzel, our astronomical lecturer, Patrick So, our astronomical theater programs manager, and Tony Cook, our astronomical observer. So, and this is an empty chair, but it's going to be filled later with a special guest. How many of you came tonight because of the special guest? All right.
Yay.
Oh, special guest fans. Okay, excellent. I have a couple quick announcements I try to remember to make every time. One of them is that if you need to leave before the break happens, we're going to take a break in about an hour. It's a little difficult to crawl over people, so hopefully you don't have to. But if you do, please go out the back, not the front. That goes to a closet, and that's an emergency exit that will take you outside, and then you'll be completely lost and confused, dazed and confused. So please go out the back. Don't use these front exits. If there is an emergency, we'll lead you out there. And if you have a cell phone on, you might as well turn it off because you're not going to get any signal in here and you'll lose all kinds of battery as you're roaming. We are protected by this magical, actually it's physics, screen that keeps radio signals out of this space, so you won't get any signal here. And before we get to songs and swag, have I forgotten anything other than to thank our sponsors? Yeah, so to thank our sponsors. LiveStream. Hello, LiveStream. Hello, LiveStream. I forgot. I didn't forget. I just had, I didn't forget you. Welcome, LiveStream people. We're off to a great roaring start tonight. So I do want to ask how many people here are members of Friends of the Observatory? Thank you very much. Don't you wish you were raising your hand if you weren't? It's so easy to become a member of Friends of the Observatory. You go to their website or our website that has links to their website and become a member and support all the programs we do here, including our wonderful 5th grade school field trip program. And who doesn't want to help 5th graders have a cool field trip, right? So especially if you've come many times, and this is free, so think about becoming a photo member. Then you get invited to their holiday party and lots of other benefits. So think about becoming a member of Friends of the Observatory. And how many of you are tax-paying citizens of the city of Los Angeles? Yay, tax-paying citizens of the city of Los Angeles. You pay my salary, so I'm grateful to that. And everyone here, we're all employed by the Department of Recreation and Parks that owns and operates Griffith Observatory on behalf of the city of Los Angeles. So we're a municipal observatory. Not a lot of cities have that, other than Springfield, if you've seen the Springfield Observatory. For yes, any of you fans of Homer and Bart Simpsons. Anyway, it looks just like it's patterned after Griffith Observatory. So. And so anyway, we very much appreciate the support of the city and by extension the support of the tax-paying citizens of the city that make all of this possible. So with that, let me just say you probably heard some music coming in, and our friend Bill is going to tell you what you get for that. So hi, Bill.
Yes. Hi. Yes, you heard music coming in. We play a little game called Name That Tune, Story, Relationship, Connection. We got to come up with a better title. It's each song that you heard or piece of music is related to some specific story, thematically or words or somehow. And if you make that connection as the story is coming up to be told, go ahead and shout out the name of the song, or if you just know the band or something that identifies it, and you win a prize. Now the prizes are incredible. You all got a prize coming in today, I believe, because of our wonderful guest speaker on the Europa mission. But we also have a New Horizons patch, Explore Mars patches. We have all sorts of things. We actually have a little. Yeah, a little, in case of an earthquake, we have a little flashlight here. I've never been able to give that away. I'll probably take it home someday. We have a pair of 3D glasses. These are state-of-the-art red-green, separation. But we have some stickers of various solar system objects. We also have calendars. They are beautiful calendars. They have one little flaw, and that is that they're all out of date. But out-of-date calendars can be reused, and I'm going to tell you about this. We have this is Griffith Observatory architecture. It's brand new. I mean, it's 2008, I believe. Yes, 2008. It's a brand new 2008 calendar, which will be good again in just 18 years in 2036. We have Griffith Observatory calendars from 3 different years, 2015, 16, and 17, which will be good again in 2026, 2044, and 2023. So you throw them in a sock drawer and put an alert in your phone and all of that, and it comes up. There's also one more calendar that strangely has absolutely no year marked on it, but it's huge, it's beautiful, and I believe it's a 2008, which means it'll be good again in 2036, as I said. I'm not sure. No, that was 2016. Anyway, calendars. So enjoy the show.
Thank you, Bill. As the little sign says, the first Friday of every month is All Space Considered Friday. Today is Friday, September 7th, and this is what we have in store for you. Parker on its way. I think some of you might know what that is. Tally-ho, thully. I don't even understand that one. I have to thank Jared here, who usually comes with most of these names. Oppie, can you hear me? Sky Report, and then, of course, our special guest, Dr. Robert Pappalardo from Jet Propulsion Laboratory, who's going to tell us all about going back to Jupiter, in particular Jupiter's moon Europa, and why that's such an exciting target, and what we're going to learn in the next decade from the mission for which he is the chief scientist. So he's the top dog scientist. You're hearing it from the top dog wherever you are, Robert. I don't mean to refer to you as a... Okay. And then it's break. Pretty pictures, of course, and then break. And that's about a 10-minute break. Then come back in for part 2. And Dr. Reitzel here at a fire on the playa. I'm sorry. Yeah, he was at Burning Man, so that's what that's all about. He's going to tell us about it, kind of a cool astronomical installation. Iced moon, not iced tea. Too little water, too much fire, Antarctica melts. I think you see a theme forming here. And I can't even read that one.
Sauna Earth.
Oh, Sauna Earth, all on the same theme. Anyway, you can read the last ones, because I really can't. And Wormhammer. Okay, let's move on. Oh, is that what that is? Okay, some jokes I just don't get. So if you've been to All Space Considered before, you know that we often like to start All Space Considered with a launch. So we have a launch of a Tesla. You bet, a launch of a Tesla. There it goes. Yeah. So, yep. And as Bill was careful to remind me, it's a suborbital flight. But anyway, kind of cool footage. We just
It looks
thought
like
that
it landed successfully.
it did land successfully. But no, we in fact have a really, really fiery launch for you of the Parker Solar Probe.
6, 5,
Good launch to start with.
3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
Core booster is throttling down to the partial thrust mode.
That's a lot of thrust.
All right, well, that was the long-awaited launch of the Parker Solar Probe, which happened on August 12th. It was delayed just one day, but it still got its launch into space and is heading towards the sun. Now, it was launched at night, and this always confuses people because, you know, the sun's not up there. And they always ask those questions about why didn't launch during the day? Well, you can figure out.
Because it's more beautiful at night.
Yeah,
right.
of course, yes.
Yeah.
So the Parker Solar Probe was actually dedicated to Dr. Eugene Parker, famous solar astrophysicist who characterized solar winds and the sun's corona. And he was up in that upper inset there. He was there to watch the launch of his solar probe. Now, what's going to happen in the next few months? Well, the probe is heading towards Venus, and it will do its first flyby on September 28th. And Venus will act to slow it down like a handbrake. So the probe will then go towards the sun and do its first flyby close to the sun on November 1st. The mission is seven years, and it consists of 24 orbits. So with each successive flyby, the Parker Solar Probe will get closer and closer to the sun. So it starts at 15.4 million miles, and it gets as close as 3.8 million miles, which is 9 times closer than the orbit of Mercury. Now, at that distance, not only will the sun appear big, it will be about 25 times bigger than what we see from Earth, but it will experience some fierce temperatures. So on the front side, where there's this shield, it will experience a temperature of 2,500 degrees Fahrenheit. All the instruments behind the shield will be at about 85 degrees Fahrenheit, so kind of like a normal day here in Los Angeles. So the science will take just about 11 days when it's close to the sun, and then the rest of the time it will be actually downlinking all the data it will gather back to Earth for scientists to analyze. I'm going to go to the next slide. Something very interesting about the solar panels, they will actually be open only about 1 inch when the probe is very close to the sun. And that's because at that distance, the sun is just about 625 times brighter than what we see on Earth. So there's ample light there. And it's made with material that can withstand the 2,500 degree Fahrenheit temperatures. When it's far away from the sun, the solar panel will deploy fully, and because there's less light, and that will generate the electricity it needs to operate its instruments. The probe will join a fleet of other spacecraft which are currently studying the sun, so we can't wait until December 1st to get some of the data back from the solar probe.
So NASA made a little video about it, and we thought we'd offer a little help. Very grand.
Parker Solar Probe, humanity's first mission to touch the sun.
Tastes like burning.
It's humanities. So, as Patrick mentioned, it's going fast, really fast, and it has now surpassed the New Horizons mission as the fastest thing to leave Earth. New Horizons had to get really cranked up to go all the way out to Pluto and beyond, but of course, as it goes farther and farther out into the solar system, it loses speed because the gravity of the solar system is tugging on it. Parker Solar Probe gains because it's falling into the potential well of the sun in the center of the solar system, so it has to slow itself down to give away some of that energy. By the time it gets at its closest perihelion, it is traveling fast enough to get from here to New York in 25 seconds. So it's very, very fast. To go from fire to ice, our other next spacecraft story is about the New Horizons mission, which went past Pluto in July of 2015. And it has been cruising on its way after Pluto to the outer solar system, to the Kuiper belt is the name of it, where all the little tiny Kuiper belt objects, or little proto-comets, things that become comets if they fall into our solar system, fall inward toward the sun. And so the Hubble telescope did identify this target for New Horizons. There it is, you can see with a little green circle. That is MU69. But it was recently given the name Ultima Thule. I think that's actually not its official name, but that is what it's being called. And what's exciting about this is that we have just this last few weeks, 2 new views of Ultima Thule. I always feel like, multipass when I say that. But anyway, so one is through an occultation observation. And just to clarify, an occultation is when an object, a star moves behind an object, or more properly, an object moves in front of a star, whereas a transit is when something small passes in front of a star. So, so through an occultation, and here's a little example of an occultation of Venus. Venus moves in front. In the background, you see disappearing behind the disk and reappearing. That's basically, it's as though you were measuring the brightness of the background object. It would just blink out and blink back on. So when you do an occultation observation, depending on where you are on the Earth, you have a slightly different angle, and you have a little bit of a different part of the asteroid or thing that you're trying to observe block out the light. So here's a picture of a beautiful example of observations of the blink off, blink on by several different observers at different positions on Earth, not too far spread apart, but enough that they get different. The shadow gives you a sense of what the shape is. So here's a nice little binary asteroid that it saw. Now, we did this once before in 2017. We, meaning the team that was observing, because they want to know, what is this object going to look like when we get there? What do we need to know about it? How big is it? How massive? It helps plan their observations. So there's the observation that blinks out. There it goes. There it is. 1 second. Just blink off, blink on. Clap off, clap on. And so the data from that occultation looked like this, and it kind of looks like a Mickey Mouse or something. I don't know quite what with the ears, but in fact it could also be described by 2 circles. So the question is MU69 a binary? And we need to keep observing, then finally get up close to take a look and find out, see whether it is. So another occultation expedition went to Senegal just in August, and if you came to our talk with David Grinspoon and Alan Stern, they talked about this upcoming. So it has happened. Here's kind of a cool little fast sped up version of them doing the work, setting up camp, getting ready to make these observations for the occultation. Now they haven't released their results yet. But they had success, they had clear skies, they got data, and so we're waiting to see what the next occultation study what tells us about Ultima Thule. So the other new observation is that New Horizons actually acquired its target. And here you can see, there it is in the yellow crosshairs. That's where New Horizons is headed. And so we just have to wait until the end of the year, to December 31st. Yes, it's New Year's Eve. You don't want to go to a party, you want to watch this, or maybe have a party and watch this, which is probably what I'll do. So very exciting. Just coming up, we'll get our first close-up view of a Kuiper belt object ever. So onward with New Horizons. So a little closer to home.
Yeah, a little closer to home. Opportunity. This Opportunity rover on Mars. It was a 90-day mission that's now on its 14-plus years. Although there's been a little problem. Mars has been covered in a massive dust storm, and it was so thick the solar panels stopped generating enough electricity for Opportunity and went silent.
Wake up, little Susan.
That's a good one.
It's a great one. So yes, come down and break and get a prize. But the dust has been settling, and there's hope that maybe, cautiously optimistic, scientists are hoping that we might be able to hear from Opportunity again. Although they are also setting a time limit. If the dust levels, the opacity in the sky, as astronomers call it, drops to a value of 1.5, they're going to start a clock, because they feel if it drops that low, the batteries should start charging if there's not a thick layer of dust on those solar panels, and it'll go into a reboot state and try and contact the satellites that are in orbit at Mars, and then they'll contact back to Earth. but they're going to give it 45 days. So if the opacity drops to 1.5, a clock will start. 45 days later, if they still haven't heard, they have to send their main team home. The people will get reassigned to other missions. However, they'll still keep listening. They aren't going to just stop listening altogether. After 45 days, they'll try and hear. But they are optimistic, and we hope that we will actually be able to hear from Opportunity.
Okay, so Tony, you want to tell us what is in the sky this
so
month?
let's see what's happening in September in the sky. And one of the big things that happens in September is we change seasons. So.
Or season.
Yep. There we go. But which season?
People are on point tonight.
I know.
Wow.
The prizes are going fast and furious.
Yeah, so on the 22nd of September, right after sunset, actually just a couple of minutes after sunset, autumn begins. And it's just when the sun crosses the equator of the sky, moving from north to south. On that day, the half the Earth, well, I should say from the North Pole to the South Pole, half of the Earth gets illumination and half doesn't. So days around the world are pretty much 12 hours long, and nights are 12 hours long.
So
equal
equinox,
nights.
yeah.
Yeah. So anyway, that's one thing to look forward to. And we'll have events here. We usually have a noon event when the sun crosses our Gottlieb transit corridor, and you can actually see the event happen on a large chart, and also see the sun projected. It's really exciting. And then at sunset, we'll see the sun set directly west and explain to you what's going on. Anyway, the planets are kind of arranged in a huge bow across the sky from the west-southwest to the southeast. And the moon will help you find them this month. So if you look around the 11th, you'll see Venus down low in the southwestern sky with the moon near it. And the moon will pass by the different planets. Here it's going by Jupiter on the 17th, Saturn I'm sorry, jumped ahead.
Yeah.
On the 17th, and then Mars on the 19th. There we go. Perfectly coordinated.
Yeah.
Now, Venus right now shows a crescent through a telescope. Now, if you look with your eye, you're not likely to see much detail other than the phase. But using ultraviolet and infrared filters, amateur astronomers can record the cloud features, which you see in the color view in the lower right image. Now, Jupiter is visible for a brief time in the evening. If you want to see the red spot, this is kind of the last month you'll be able to this year, because Jupiter will pass behind the sun in November, and before then it will be too low to really get a good look at. So we are showing it, and Venus, with our telescopes on the lawn currently. Saturn is absolutely gorgeous, and this is probably the best time to see Saturn early in the evening because it's high almost in the south. And this is also a favorite. It's said that Colonel Griffith, having looked at Saturn with the 60-inch telescope at Mount Wilson, was so impressed that he had to give that view to everyone. So that's why this observatory is here. So we always love showing Saturn, and people love seeing it. Mars, this is a recent view by Clyde Foster of South Africa, where Mars is overhead in their sky. And here you do see the clearing view. The color image is a composite of all these different filtered views. And in fact, we are seeing more detail down to the surface. The dust is settling, and that's why we hope to hear from Opportunity soon. The moon, this coming weekend is actually the new moon weekend, and that's great timing because of another event that's going on. Go to the next picture here. In the early morning, the brightest star up in the northeast sky is a star called Capella in the constellation Auriga, the Charioteer. But Capella is as bright as just about any star in the northern hemisphere. Only Vega in the summertime is equal to it in brightness. And near it is a comet. So that actually makes it easy to find. If you are able this weekend to go out to a dark sky, like out in the desert or high in the mountains, bring binoculars, and you shouldn't have too much trouble finding a comet. And this comet is called Jacobini-Zinner. It's also 21P because it's the 21st comet whose periodic orbit was calculated. I saw it back in 1983. I think it was a practice comet for Halley's when NASA had the International Halley Watch. So we all watched Giacobini's Inner. And it actually turned out to be a really neat comet. Through telescopes, you can see a lot of detail. There's a long, slender tail. You can see what's called a pseudo-nucleus. We can't see the actual nucleus of a comet because it's too dim and too tiny. But the dust that it throws off in the gas lights up the area around it, and then it forms a huge atmosphere called, or an exosphere. It's actually leaving the comet, called a coma, and then the tail. So in a telescope, you can actually see this. This is a recent drawing by a German amateur. That's why it's spelled with a K. And that's what it looks like through an eyepiece. And then the next few photographs show cameras, of course, can record color and other details even your eye can't see. So this is how it photographs through a telescope. And it's passing, Auriga, the charioteer, the constellation it's going through, is filled with lots of star clusters. So there's, this next picture shows the kind of beautiful images you can have if you're skilled with taking astrophotographs.
Okay.
And finally, here's a recent image of Jupiter by Damien Peach of England.
So I asked Tony to give us a recent picture because while Jupiter's kind of nice, what's really cool from tonight's perspective are some of these moons. So with that, Europa, the second I Eat Green Cats, we never forget that, Eat Europa, is... Mike is my cat. Anyway, being visited hopefully early 2020s, and with us tonight is Dr. Bob Pappalardo. So let's welcome Bob.
Thank you. Thank you. It's a pleasure to be here.
And it's such a pleasure to have you here. We've known each other for an awfully long time, and we've talked about having you come for an awfully long time. So it's finally happened.
Great to finally be here.
And I'm really happy you're here.
What fun. And then I get to talk with you about one of the most exciting places in the solar system, Jupiter's moon, Europa. And why is it so exciting? Because it's like really no other object out there, and because we believe that there's a subsurface globe-girdling ocean beneath Europa. Let's see, show me what to do here. There we go. Whoops.
It's upside down.
Let's try that.
Oh.
Even better. There. And we'll see Europa a little bit, and then we'll also talk about the mission to get there that NASA is finally doing. After many years of working to get this mission started, we even are premiering here our new beautiful model of the Europa Clipper spacecraft, which we'll talk about in a little bit. So Europa is one of the 4 big moons of Jupiter, a lot of little ones, but the 4 Galilean satellites, Io, Europa, Ganymede, and Callisto. Ganymede and Callisto are kind of half ice and half rock. Io, as you know, is a rocky object and the solar system's most volcanically active body. Europa is kind of in between. It has a density that tells us it's actually mostly rock, but there's a skin of H2O, some of it frozen on the outside, and we're pretty sure some of it liquid on the inside. So there's Europa closer up. You know, most moons you look at and they're covered with craters. Europa has very few craters. One of them you can see in the bottom there, and it's called Pwyll in the bottom left of the image up there, or Puch if you're Welsh. Can't quite get that right. The bright areas of Europa, especially near the poles in that global image, are covered with ridged plains. So places where ridges and grooves are cutting across the surface. We don't really understand how these features form, though they're the most common feature on Europa's surface. It might be ice sort of oozing up through fractures, pushing up the surface above. There are these chaotic terrains. Those darker areas are aptly named chaos, places where the surface seems to have broken apart, probably because of heating from below. And when we see smaller spots, we call them lenticulae. That's Latin for freckles. And we think they have to do with churning of the ice beneath, as we'll see. This is what we think Europa's innards look like. And we know that from gravity measurements that tell us that Europa has probably an iron core down there and a rocky mantle, and then about 100 kilometers worth of H2O. And we think about 20 kilometers of that is ice, and that would leave the remaining 80 kilometers or so for water. Now, we're not sure. You know, these are estimates based on, well, gravity data for the interior structure there, but then geologic features and arguments from thermal models as far as how thick the ice is. So we really don't know very well, and that's part of why we're going there, to understand that. Europa's ocean, the volume of it, is probably on the order of twice that of all the Earth's oceans combined. You can see little balls of water there that represent piling up all of Earth's oceans in one volume. Europa is probably about twice that. Now, how do we know there's an ocean down there? I'm a geologist, so I like to think we know it from geology. We have indirect evidence from geology that we'll see. But the most direct evidence is from the magnetic field in the vicinity of Europa. So Europa is orbiting Jupiter, and inside of Jupiter's giant magnetosphere, area of magnetic influence. And Jupiter's magnetic field is tilted. That little movie is showing that as Jupiter rotates around, the tilted magnetic field sort of flops and wobbles, and Europa is minding its own business orbiting around Jupiter, and it's feeling a changing magnetic field. And in response, Europa is generating its own little magnetic field that is swinging around to counteract Jupiter's. Well, that means Europa is behaving as a conductor, something that's essentially conducting electricity. And metal can do that, but the metal core is too far away. So we think what is conductive here in the shallow subsurface is a salty water ocean within Europa. So indirect, but very convincing evidence of an ocean beneath Europa. Let's see, we'll click the little movie to make it go here. Not to scale. That's illustrating Europa orbiting Jupiter, just like Io does, in a somewhat eccentric orbit, getting farther and then closer to Jupiter. And as it gets closer, it gets stretched out, and as it's farther, it contracts back a bit. This happens every 85 hours. Every 3.55 Earth days, Europa is orbiting around Jupiter and getting stretched as much as 30 meters as it orbits around Jupiter in 85 hours. And so friction is going to mean that generates heat. And as we look at the other movie here, also not to scale, we can look at it from Europa's perspective. Europa is getting stretched out and actually nodding back and forth, librating as it orbits around Jupiter. So this tidal kneading of something like 30 meters every Europan day is generating heat in there. Enough heat to maintain a liquid water ocean beneath an ice shell something like 20 or 25-ish kilometers thick. We don't really know if the interior, if the mantle is hot or not. It depends on how squishy, how warm, how deformable the rock is. It's a little of a chicken and egg. If it starts out warm, it can stay warm. If it starts out cold, it might stay cold down there. Let's see, there we go. Whoops. There we go. We looked at those freckles earlier, the lenticulae. Those seem to be a sign that the ice shell of Europa, that 20-ish kilometer thick layer, is kind of oozing like a lava lamp. Okay, some in the room are old enough to remember lava lamps. Lava lamp?
Absolutely.
Of course you do. So now in a lava lamp, warm wax rises up through oil, and there's a light bulb down there. So there's no light bulb on Europa, but there's the tidal heat. That squeezing generates heat, and that heat is input mostly in the base of the ice shell there near the ocean, and that ice is warm enough that it can flow and rise buoyantly up toward the surface, and we think make these pits and spots and domes at the surface of Europa. This is a feature called a band, that red streak through the center. And when we use that sophisticated scientific tool known as Photoshop, we can cut out that band and put back together, reconstruct the surface on either side. And all those ridges match up. Let's see, must have a laser on there. That one? Oh, this one. Oh, nope. That one. There we go. So you can see these ridges have been split. And there are some old bands that have been split. And so there was a fracture, and this thing pulled apart to make this band. And you can see somewhat of a parallel structure within it. Postdoc who's working with me at the Jet Propulsion Lab, Sam Howell, he studied mid-ocean ridges on the Earth's ocean floors, places where new rock is oozing upward to fill in gaps as the crustal plates are pulled apart, the oceanic plates. And so he said he wants to come and try to model the same thing for ice on Europa to explain these bands. And he put together this fantastic animation. Now the bottom of that model is where the ocean is. The top is the surface. It's really cold. It's 100 degrees Kelvin. Someday I'll remember the conversion. Really cold. And
minus 273 Celsius. So that.
She's got it. Something like that.
No, convert to Fahrenheit.
A couple hundred. Exactly.
There's a calendar for whoever can convert that.
That's the problem. We speak metric and Kelvin.
People get their phones out.
So here the yellowish stuff is the colder near surface ice, and the bluish stuff is the warmer flowing ice. So it's a little counterintuitive, but near the base is where it's warm, near the top is where it's cold, and he runs his model for 1 million years. And when you see flowy things in this model, it's not liquid water, it's ice, because ice can flow over geologic timescales. And you'll see some white particles because it's entraining material from the ocean and bringing it up toward the surface. Boom. So he's pulling apart the model. There's convection going on, these blobs of warm ice rising up at the base and coming in and filling in that gap that's forming by the surface. Whoops, if I hit it again. Make it go again. This is so darn cool. Oh, there we go. So material from the ocean, we think, can actually get to the surface in these bands. So that'll be a really interesting place to check out with our spacecraft and maybe someday go with a lander. Then there are these chaos regions. And they're places where that icy surface has been broken up. It's as if something warm has come up from the interior and kind of cooked the surface. It's a little like a jigsaw puzzle with half the pieces gone here, where they've just broken apart. What we think is going on is there may be lakes within the ice shell, and if you melt ice, the volume's going to decrease when it goes from ice to water and cause the surface to collapse to make these chaos regions, and then that lake might freeze up and cause the surface to dome back up. So that's the current best model for how this forms, maybe related to, again, warm ice and that tidal heating going on beneath these chaos areas. Those will be fascinating places to look for subsurface water with the radar that our spacecraft is going to carry. Oh, scale, right, I didn't talk about scale. There's some familiar things. So LA would just about fit in there. There's probably less traffic on that commute.
I know, and there's a direct route from Griffith to...
The roads look just as smooth.
Yeah.
Got a little peak there. Griffith is on. We think Europa, like Enceladus at Saturn, may have plumes. Enceladus, we're sure. We can see them with the Cassini, or did see them with the Cassini spacecraft. Using the Hubble Space Telescope, there are hints of a glow of hydrogen and oxygen that have been seen on the limb of Europa several times during several Hubble orbits. So it may be that there are plumes at Europa as well, and there was a recent result that the Galileo spacecraft 20 years ago may have flown through a plume. There's a magnetic signature blip that now that we may understand what plumes look like at Europa, put that into the model, and voila, it well explains mysterious Galileo data from 20 years ago. So Europa may have the so-called ingredients for life. Liquid water, probably much more than all of Earth's oceans, in the ice shell, in the ocean. Essential elements, elements from which organic molecules can be built, things like carbon, hydrogen, oxygen, phosphorus, sulfur. They're common, we expect them there, brought by impacts over the eons. Chemical energy is a tough one. Is there the energy in Europa's ocean that could support life? Thinking back to your high school chemistry, couldn't there be redox reactions in the ocean, reductants and oxidants? Well, oxidants can come from the surface. The surface is bathed in radiation, charged particles pouring down onto Europa's surface as they're trapped in Jupiter's magnetosphere. And they rip apart H2O. The H floats away, the O stays behind. If that stuff can get into the ocean, it's a wonderful fuel for life, for microbial life. As far as the reductants, the other half of the reaction, chemical reactions between water and rock can create hydrogen-rich materials, reductants. Or, like in the Earth's black smokers, if the interior is hot and water seeps down there and cracks, it can come out charged in chemical nutrients. So Europa may have the chemical energy to permit simple life. And then is it a stable environment or is it a flash in the pan? Well, Europa's ocean has probably been there since the beginning of the solar system. So the Europa Clipper mission, we want to test these hypotheses. Some of these things we know better than others. They're the best we can do right now. We want to study Europa's ice shell and ocean, its composition, its geology, its activity. Are there plumes? And we also want to do reconnaissance for a future lander. Someday, we'll send a lander to Europa and be able to set down on some of this dark reddish stuff where maybe there are organic materials and dig down in there beneath the depth at which radiation processes the surface and scoop some of that stuff up and determine its composition in detail. But until then, we want to understand, does Europa have the ingredients for life, and are our models correct, or how do we need to change them? So that's what we're going to be doing with the Europa Clipper. There are two categories of instruments. There are 9 or 10, depending on how you want to count them, because there are 2 cameras. So first, there are the in situ instruments. Those are the instruments that measure in place from orbit their environment around them. There's a mass spectrometer that will sniff the very tenuous atmosphere at Europa, and if there are plumes, be able to sniff them and tell us the detailed composition. There's a dust analyzer. There's dust kicked off the surface. Europa's in this big cloud of dust. We can measure the composition of those particles knocked off of Europa. There's a magnetometer, IceMag, which will redo the Galileo spacecraft experiment of measuring that induced magnetic field, but in much more precise detail to get not just the existence of an ocean, but its thickness and even its salinity. A plasma instrument tells us the composition of the charged particles around Europa and is needed to understand that magnetic signature. There'll be the category of instruments circled in blue are remote sensing, so looking from afar at Europa. An ultraviolet spectrograph, so like Hubble, look in the ultraviolet to determine whether there's the glow of particles, charged particles interacting with gas that would indicate plumes. The ICE is the Europa imaging system. That's the 2 cameras. One is a wide-angle camera to map the surface, to get stereo imaging, give us topography that way, and color imaging. And there's a high-res camera that during close flybys, as close as 25 kilometers off the deck of Europa, will get images up to 0.5 meter per pixel. Yeah, it's going to be spectacular. And so we can also do nice mapping even from afar. We can look for plumes from afar. eThemis is our thermal instrument to look for hotspots, kind of like Cassini has done at Enceladus, to look for sites of activity. MISE is an infrared spectrometer, tells the chemical fingerprints of what's on the surface, a great complement to SUDA and mass specs. And last but not at all least, REASON is our ice-penetrating radar that I alluded to before. Ice, cold ice at least, is very transparent at radar wavelengths. And so we'll shine radar at Europa, it'll travel through the ice, bounce off liquid water, and back to the spacecraft. So we'll be able to plumb the ice shell of Europa, find lakes, understand if those ridges have anything to do with water, and if Europa cooperates, we may be able to penetrate all the way down to the ocean and measure the ice shell thickness directly. So there's our little spacecraft, this model, and in this illustration.
How big is it really?
Well, from tip to tip, it's about the size of a basketball court.
Tip to tip of the panels?
Of the solar panels.
Okay.
That's right. So a person would be, maybe this big next to the Europa Clipper
LeBron
spacecraft.
James would be that big.
The high gain antenna, which is covered with a dome here, is 3 meters across. So that'll give you an idea of the scale. The magnetometer boom that sticks out the back there is 5 meters tall. The cameras and spectrometers, the remote sensing instruments, look downward as we fly by, while the mass spectrometer and the dust analyzer look forward. And the radar antennas are on the solar panels. So these long metal rods on the model here are the long wavelength radar, and the shorter wavelength radar hang off the solar arrays. So this is a big deal, to put an instrument and integrate it right into the solar arrays. But we realized the electromagnetic influence of the solar arrays was a challenge for the radar, and let's take it head on and think of these as a system. And so the Flyby configuration is shown up there. So you have to tilt this little model and move the solar panels to put them in that Flyby configuration. The solar panels move together. So when we're not doing a flyby, we're tracking the sun to power the spacecraft and charge up the battery, and then we go in for the flyby and gather lots of data all at once and zoom on out. So we're in orbit around Jupiter. The sum of the orbits is shown there, and we're flying by Europa something like 45 times. The colors there are showing the buildup of radiation as the orbit goes on to our maximum of 3 megarads there in red.
Where's the spacecraft being built?
It's being built at JPL.
Yep. It's going to be launched by a Delta?
As far as launch, it could be a conventional rocket, a Delta IV Heavy, or a Falcon Heavy, or it could go on the new SLS, Space Launch System. And if we go on a conventional rocket, a Delta IV Heavy or Falcon Heavy, it'll take almost 8 years to get there, because we have to do the celestial billiards by the inner solar system to get gravitational slingshot out. However, on the SLS, we can go direct, 3-year travel time. Okay? So one of those is past my retirement, and the other isn't. So you know what I would favor.
That's not happening. You can't. You have to.
This illustration is showing those This illustration is showing those flyby trajectories. And this schematic, this is our current tour. It's going to change over time because we're working to optimize. And you can see as we do these flybys at different latitudes and try to cover all of the surface as best we can. Now we can't quite cover the leading and trailing hemispheres as well, because then we'd be flying right into Europa, which we don't want to do. Yes, and planetary protection will not allow us to do that. We have to guarantee that that's not going to happen. I left Jupiter going by. Planetary protection is not the reason we can't orbit Europa. We were originally looking at a Europa orbiter concept, but then we're bathed in the radiation all the time we're there. This way, we dip into the radiation and we get out, right, and transfer the data back.
Like Juno.
Yes, analogous to Juno. Juno has the advantage that they're out of the plane, whereas we stay in the plane, so it's even worse in the plasma sheet. On the right are shown coverage maps from the various remote sensing instruments, the radar tracks in the top one, and then the various other remote sensing instruments. So those are the kinds of details we're working.
Would the ice shell protect anything that might be in the subsurface ocean from radiation?
The ice shell, all you need is about a meter of ice to stop all the radiation. So even 10 centimeters of ice stops most of the radiation. Over time, you know, some will penetrate deeper, the more energetic particles.
Is radiation the primary limiting factor in the length of the mission?
Radiation is a limiting factor in the length of the mission, as is the lifetime of the solar rays. The solar rays will degrade over time because of radiation. And so power will become more and more of a problem as the mission goes on. So we're planning to make sure we have enough power at end of mission. That's how we plan these things. That means at the beginning we can transmit lots of data, do lots of cool things.
And how will you scuttle it? At the spacecraft when it's done for planetary protection?
At the end of the mission.
Yeah.
The current plan is send it into Jupiter.
Into Jupiter.
Like Galileo was. Carl Sagan says it's okay, and the planetary protection officer says it's okay. Though there has been discussion of whether it's okay to crash into Ganymede and Callisto, because there's not going to be, we're not contaminating any environment where we could someday go to search for life. That's not going to be the case at the surfaces of Ganymede and Callisto anyway. Europa, yeah, we cannot go near, and we have to show that we're not going to contaminate Europa's ocean with any microbes. So let me finish with this very cool animation of the spacecraft flying by Europa. This is just a still shot from what you'll see of the various instruments as they're looking down and doing their things, and as the spacecraft's turning and the solar rays are moving around. Let's see if this will play. Whoops. Oh, let's go back. It needs a click. So it's just transmitted. Whoops. Was that me?
No,
it's data to Earth. It's doing an ultraviolet scan of Europa as we put the nadir deck, as we call it, facing Europa, looking for plumes and analyzing the atmosphere. Which instrument is on is being shown on the bottom left, and also at the top. The magnetometer and the plasma instrument are on all the time. There was a little thermal calibration. The panel's turning there and putting us into the nearly the flyby configuration. We'll see the panels rotate when we're actually in the flyby configuration. Some of the instruments don't scan themselves, so we do a scan with the spacecraft when we're far out there for the ultraviolet and the thermal instrument, and to get a global color image. You can see the flashes of the high-res camera, the thermal instruments staying on, and the ultraviolet image spectrograph staying on. Wide-angle camera pictures of Europa flashing by. Now we rotate to put the radar antennas into the standard close approach position as we turn on all the instruments at once and zoom by Europa. And that's way sped up, of course. On the way out, we rinse and repeat. We kind of do it backwards. And then get ready to transmit all that data back to Earth. It's actually turned out to be a challenge for the avionics, the electronics, to get all that data that's being generated through and into the computer memory that quickly. There's the joint scan again. We try to keep the operations as simple as possible, and that's why we want all the instruments to be able to observe at once and to do a similar thing on each flyby, though tailored somewhat for each flyby. And also taking the data all together means, well, scientists don't argue about whose turn it is, and because then we get the best science by being able to observe the same things with the suite of instruments and think of them as complementary and getting us all that information that we can take back and analyze and make available to the science community and to the public. So that's a snapshot of where we are with the Europa Clipper.
So before we take questions from the audience, I just want to know a little bit about the status of the mission and also a little bit about the history. Like, when did it begin? When did you start working on this mission? We always like to see how lives are shaped around them.
It's been a while.
And then also just in the arc, you know, are you locked with your spacecraft? Do you still have time for changes?
Right.
You know, what's the calendar? What's the timeline? What are the milestones that we should be looking for?
We just went through what's called the preliminary design review, and we're waiting for the formal report from the board, which goes to us and goes to NASA and says how we did. Overall, a report out from the board was very positive, and this is the time where NASA says, "Yep, okay, ready to go start building," right? So that's this big review. And there'll be some confirmations and the like and reviews that happen between now and the spring to give us the go-ahead. The mission started, boy, it's been such a blur because we're rushing toward launch, right? The earliest launch would be in summer of 22, and every day we're working hard to get there. I got involved in my first Europa science definition team in 1998. And I moved to JPL in 2006 because it was clear that to get a flagship mission going, they needed someone to really push it forward. I was at University of Colorado at the time as a professor, and essentially got an offer to come to JPL and help get this mission going. I said, okay, I'll go to JPL for 3 years. If it doesn't get going, I'm going to go back to academia. We got the go-ahead from NASA to start the mission 9 years after that in 2015. And so we're on our way. Exploring the outer solar system is not for the faint of heart. It really takes dedication. And you can't just think about, you know, oh, are we there yet, right? It has to be about the journey. And it has to be about enjoying what you're doing along the way and building a team of people that you want to be working with until 2030 or so. And we've got a fantastic science team and a great engineering team. And looking forward to all these years together and then finally getting there.
So are there questions from the audience? Yes.
And when the difference between the launch vehicles you mentioned, does that affect the spacecraft or your design at all, or will the same thing on either type of?
The fact that we've been working to ensure that we're compatible with any of those launch vehicles. And so we've made the spacecraft so that no matter which of those launch vehicles we're on, we'll be okay. And the limiting case is the SLS Direct in terms of the mass. There's a little configuration issue because the Falcon Heavy would, we'd be testing sideways and then they'd lift us up. That's the level of detail we're looking at it, and relatively trivial. But yes, we're making sure we're compatible.
Does it have an electric or chemical propulsion system on board, or can we discuss propulsion?
Oh, yeah, well, we have our thrusters on board in terms of the hydrazine propulsion to maneuver the spacecraft, if that's what you mean. So, so yeah, we have. I'd have to go back to the diagram, but that's okay. We have many thrusters and engines along the bottom of the spacecraft. I wonder if I can point them out here on the bottom of this illustration.
Okay. Yes.
Yeah, I was wondering about the color of the moon, the reddish kind of color and the white. Does that have anything to do with the iron core and the salt?
The ruddy color of Europa, really this color is exaggerated when you see these images. It's probably a pale ochre in reality. And we think it's probably related to sulfur contaminants, or it might be from radiation darkening of sodium chloride. Regular table salt might be a component of Europa's surface, and that browns from radiation. So those are kind of the M-member models, sulfur compounds and or sodium chloride that are brownish in the radiation environment.
just curious, the image that we're going to see when it's circling, will it be comparable distance-wise to what we saw of the image of Pluto?
Will be much closer to Europa than New Horizons was to Pluto.
We'll see more detail.
We'll see a lot more detail. The New Horizons images were, I think, on the order 60, 70-ish.
I just remember the
meters per
size
pixel.
of the lake in Central Park. That's what Alan told us when he was here. So you could see the lake in Central.
And we'll get up to half meter per pixel. So think more in terms of high-rise, the high-rise imager at Mars, in terms of the level of detail for some of those closest images.
Yes. Yeah.
How does it happen that some objects in the solar system get a lot of water and some don't?
Out in the outer solar system, when the planets formed, there was lots of H2O, right? And the H2O in the inner solar system, right, didn't condense. It was just too warm. And out at Jupiter, near Jupiter, it was probably too warm for a lot of H2O to condense. And then farther out from Jupiter, out by Ganymede and Callisto, a lot more H2O condensed out. So Jupiter's system is kind of like a mini solar system in terms of the temperature through it when those moons were forming. And out at Callisto, you can get a lot of CO2 ice, which condensed out there. And then if you go farther out in the solar system, like at Pluto, you start getting things like nitrogen ice and methane ice, things that condense at much, much lower temperatures.
Yeah. No, you go ahead.
The sulfur you referred to, did that come from Io?
One idea is that some of the sulfur comes from Io, so some amount of it probably does. But the dark reddish stuff correlates to where the surface has been breached in some way, where we see big impact structures that penetrated deeply, or where those bands are, right? So if stuff's coming from Io, it wouldn't preferentially land on the places where material has been exposed. So there's probably some from Io, but it's probably coming from Europa's ocean, from its interior.
When will the first and last flybys be?
When are the first and last flybys going to be? So if we launch in 22, and if we're on the SLS, then we're late 25 arrival, and then I think that puts us to the first Europa flyby sometime in 26. I don't know exactly. But then it's about 2.5 years of making flybys of Europa, about every 14 days, when we're really swooping by. It takes the first few or big looping orbits. And then there are some where we fly by Ganymede and Callisto while we're changing over, because we're going to do the anti-Jovian hemisphere first, the hemisphere of Europa facing away from Jupiter, and then change the orbit and do the hemisphere that faces Jupiter. And I don't have the dates memorized because we're sure it's going to change, because the tour will evolve over time.
Yes, up there all the way in the back.
You were talking about some of the different kinds of ice that's out there in the solar system, like carbon dioxide ice and methane ice. How do we know that Europa is just water ice?
So how do we know Europa is just water ice and not these other more exotic ices? The Galileo spacecraft flew by Europa about a dozen times from '96 to the last one must have been in 2002-ish. And it had an infrared spectrometer to tell us about the spectral fingerprints of the surface. Plus, from Earth-based observations, we knew of water ice there. From the Galileo spacecraft, being closer and getting higher resolution, the Galileo scientists found some evidence of a little bit of CO2 ice on Europa. So there may be other more exotic ices, but you wouldn't expect things like ammonia or methane. Is probably just too warm in the Jupiter system for those.
All right. Yes, Larry?
Why Europa versus some other targets, say Titan or Enceladus, or multiple targets?
so why Europa instead of other icy moons? I want to explore them all, right? We're going to get there. We've got to start somewhere. And Europa has probably the greatest potential for life in our solar system. And you can get into debates with the Enceladus folks a little bit. Enceladus is an exciting place too. The question is whether Enceladus has gone through a burst of activity, or is it recent activity? Has there been enough time for Enceladus's ocean to simmer and life to form? But also this mission got going, or at least the concept and the studies got going, and we're way ahead of Enceladus and Titan because Cassini came along later, and so we and only recently finished. So it took longer to really understand those moons and understand the best ways to explore those moons. So they're next in the outer solar system queue.
All right, I have time for one more question. I feel like I've shortchanged this side of the house. Is there? Oh, they're all frozen now. All right, we'll take the hand in the very back.
Was there any?
Yeah.
Was there any consideration for a probe to drop down on the moon?
We did consider options for probes, landers. Was there something that this mission, the Europa Clipper, could carry? To get to the surface is challenging. So Titan, big atmosphere. It's actually relatively easy to put a probe down on the surface. It's tough at Europa where there's essentially no atmosphere to help with braking, and so you need propulsion. So you have to carry all that propulsion with you to slow down a probe and have it land safely. So we did look into that in detail, and to get even really a small package onto the surface would essentially double the mass of the Clipper spacecraft to get something like, I forget what it was, somewhere between 5 and 20 kilograms down onto the surface.
And I'd imagine the planetary protection people wouldn't be pleased.
I have been wondering about that with regard to Titan, as a matter of fact.
Well, Titan we're not as worried about in terms of planetary protection, the cold surface environment. And an Earth organism probably wouldn't multiply in an ethane, methane lake. But in terms of a lander, yeah, we have to very carefully think about planetary protection for a lander, where one idea is you carry an explosive and you blow the thing up at the end so that the radiation environment sterilizes even the innards of the spacecraft.
Or causes mutations in them.
Nothing's going to live at the surface. The issue is
Stanley first.
The issue is you don't want to bury organisms and then they're in a chaos area and scooped into the interior.
Yeah. Well, I know there are other questions, but we are out of time, and so let's thank Bob for coming by and telling us all about it. So in a minute, we're about to go look at some pretty pictures, and Bob, you can just hang out until the break. But before we go to break, I just want to comment that there is a talk coming up on Wednesday, September, that looks like a 12th, about the Orion mission at the Orion spacecraft at the Burbank Library. And I think, Hubert, are you here? Yeah. There. This gentleman knows more about it because he's the guy who's organized it. So if you want to hear more about it, you can speak to him at break. So with that, I think we will say goodbye to our live stream audience because we're about to turn off the lights and look at pretty pictures.
Bye, Mom.
Bye, Mom. Oh, yeah, good point. Bye, fam. Anyway, so thank you for joining us, and thank you again, Bob. And with that, we'll sign off live stream and take down the lights and look at some pretty